this video, I will discuss the Laplace transform. If you are following along in a first course in differential equations textbook by Dennis Zill, this will be chapter 7. Before I discuss the Laplace transform, I want to build your intuition to give you an idea of what our transform, the effect that it will have. So John Napier, known as the father of logarithms, was known for simplifying calculations. So today, now that we know what we use logarithms frequently, you might consider a very difficult product. And suppose that you didn't want to do that difficult product, say it had several digits, suppose you didn't want to do that by hand. What you could do is take log of both sides. So what I mean by that is, say that you had something like 9,000 times 810 and you just didn't want to do that math. Then what you could do is maybe take log of base 90 of the left hand side. Now on the right hand side you don't know what your value is, you could call that x, so on the right hand side you might have log base 90 of x, but on the left hand side you could simplify that down using log rules. So log of a product, you can rewrite that as log of the sum of two logarithms, etc., so that some of those values you would have a simplified expression on the left. Once you've gone as far as you could with the logarithms, then you could go back to your original calculation by using the inverse of a log, so an exponential function. You could exponentiate both sides. So John Napier was known for simplifying these calculations, kind of transforming a calculation using logarithms, and then he would revert back, so use the inverse, so exponentiate both sides to correct for that transformation. Now this allowed for an easier method, but it was still the exact same solution that we were looking for in the beginning. So the reason I'm discussing this is because this is to give you an idea. We will be taking some differential equations and applying a transform that completely changes the original differential equation. However, using that transform, we'll be able to simplify a differential equation so that it is easier to manipulate, and then we'll use the inverse and still get the exact same solution. So that's where we're headed. If you read the beginning of 7.1, they will talk about integration. And so just to remind you, in Calculus 1, you may recall that integration over a definite integral is really finding the area between a function and the x-axis. Now, when I integrate here, if I integrate with respect to t, this integral here will result in a function in terms of x. And so if that sounds familiar. Now, this is not quite the Laplace transform, but we will be using the idea of integrals. And the Laplace transform will be useful for many types of differential equations. We are not using this on nonlinear differential equations, but really any linear differential equations, and as well as it's quite useful for initial value problems. So to introduce the Laplace transform formally, we will be looking at the indefinite, so the improper integral here. So I have an indefinite interval which I'm integrating over with respect to t. T is, you could think of t as time, so always non-negative here. And you'll have a function f of t, the Laplace transform of a function, so I have L of, you might see a script L, so L of a function, the Laplace transform of a function in terms of t is given to be this improper integral. Inside I have the product of f of t times e to the negative st. Now s is a new variable that I'm introducing. This e to the negative st, if t and s are positive, then this is, you could think of it as exponential decay. And so improper integrals, you'll recall from Cal 2, do not always converge. This decay factor is helping, so it's encouraging this integral to converge for us. So improper integrals do not always converge. We'll talk about what kind of functions, maybe what conditions we'll have for f of t so that it does converge. But for notation, if you might see this script L of f of t, or you might also see a capital F of s. So this right hand side, because we're integrating with respect to t, when I integrate, I'll be left with a function, because I have bounds here, I'll be left with a function entirely in terms of s. So sometimes we'll take, if we want the Laplace transform of a function, they may capitalize that f, the name of the function, and that function will be dependent only on s. To ensure that the Laplace transform exists, I need the improper integral to converge. If you consider the function f of t equal to e to the st, so e to the st times e to the negative st would give me 1. If I were to evaluate 1, the area beneath the line y equals 1 on the interval from 0 to infinity, then that would not converge. And so what I'm talking about down here, the restrictions on f of t, I must have an f of t so that I still have a decay factor here that's helping this integral converge. And so we say that f must have exponential order, and what we mean by that is it must grow at a slower rate than exponential functions. And so we don't want that canceling out. So if you see this term in the book, f has exponential order, it's saying that that product, this f of t will not be growing faster than exponential, so that these cancel out, so that this decay factor does not help the integral converge. So don't get too worried about this. I think you'll see what we mean by this when we look at some examples. Another condition would be, because we have this integration, then f of t must be continuous or piecewise continuous, so finitely many breaks there as well, and that comes from our calculus. So first we'll look at an example where we will be finding the Laplace transform of this quadratic, and this we are looking for t greater than or equal to 0. A, B, C are just constants here. I'm using this as our first example so we can maybe pick up some patterns. So just a common quadratic, f of t is a quadratic. We will be evaluating the Laplace transform. So the Laplace transform of that quadratic, I would have that improper integral of the function times e to the negative st. I want to evaluate this. Keep in mind this is an improper integral, so really this is the limit, and I've introduced a dummy variable b here. So my definite integral now, my bounds are 0 to b, and I will take the limit after I've evaluated that integral. I went a little too fast there. You'll notice that when I try to integrate at squared times e to the st with respect to t, I will need to use integration by parts twice. For bt e to the negative st, integration by parts will be necessary once. C e to the negative st, that's a piece of cake. I'm just integrating e to the negative st with respect to t. S here, because we're integrating with respect to t, we'll just treat s as a variable, or a constant, I'm sorry. We'll treat s as a constant. It is a variable, but we'll treat it as a constant because we're integrating with respect to t. So for this last term, the antiderivative of this last term will be negative c over s e to the negative st. For the first two, I'd like you to pause the video. We will have to use integration by parts, so please pause the video and maybe build a chart for both of these first two terms. After you have built a chart, we'll apply the outcome that you got. We'll apply integration by parts so that for the first term you'll see a few with a's here, so that's what is coming from integration by parts. I'm plugging in my upper bounds, so b, I've plugged in b, and then I'll plug in my lower bound 0. Now when you plug in 0, you'll have several terms that cancel, so pretty much this first one, second one, I will only be left with a negative, so that's why I have a plus 2a over s cubed. The e to the 0 will be 1, and so that's canceled. So these three terms and this fourth term all are from integrating that first. The second one, using your chart, integration by parts, you'll notice that I have the two terms here when I plug in lowercase b. By plugging in t equals 0, For t equals 0, this term will cancel. I would have had bt for my antiderivative, so this term would cancel, and here I'll be left with simply, I'll have negative negative, so plus b over s squared. For the c term, my antiderivative evaluated at b, this would be the first term, and then if t is equal to 0, then you will simply have c over s. After evaluating, so we have the antiderivative evaluated at the upper bound minus the lower bound, then you will plug in your limits. As b goes to infinity, we'll look at each of these individually. So here, b squared over e to the sb, an exponential grows far faster than a quadratic, and so this denominator will be growing at a much faster rate. Because that denominator is growing much faster than the numerator, this will go to 0, as well as this one. Linear functions have no competition to exponential functions as b goes to infinity, so the first and second term, as well as the third term, because this is a constant over an exponential, these first three terms completely go to 0, so they will disappear once we evaluate at the limit. As well as, so here I have lowercase b over e to the sb, so b and e to the sb are what we're taking the limit with respect to. Because that's a linear function over an exponential, the exponential dominates the linear function, as well as in this term a constant over an exponential function. These will also go to 0. C over e to the sb, another constant over an exponential. As b is going to infinity, this also goes to 0. Now here, because these last three terms are not dependent on b, then the limit of each of those will be themselves, so that what will only remain are these three terms. And keep in mind, all of this is depending on the values for s. They must be greater than 0, so that's something to keep in mind. But we didn't want s to be equal to 0, for instance, and so our interval, we remember with our intervals, because we have that break, we're going to choose one of those, and so we'll choose the positive. So s must be greater than 0. This will be the Laplace transform for quadratic. So you'll notice Laplace transform, we could call this capital F of s right here. And I want you to try to pick up some patterns right now. The Laplace transform of that quadratic gave us this sum. Now you'll notice I had 3 terms for the quadratic. I have 3 terms for the Laplace transform. Interesting. The at squared. So I don't quite have a derivative there, but you'll notice that t was squared and I ended up with a 2a. And in the denominator I have an s cubed, so 1 power greater than the squared term. For bt I have a b over, so you could think of the derivative of t as 1, so 1b, and then the power of s is 1 greater than that. C over s, so here, not necessarily the derivative rule, but c over, so did not have a c, or I did not have a t, I'm sorry, so I've added 1, so c over s, so t to the 0, s to the 1. Those are kind of some patterns. You could actually generalize this further, and we'll talk about that in a second. One other thing I want to point out. If you have the Laplace transform of at squared, your a remains. The Laplace transform of bt, your b remains. So the Laplace transform, like derivatives, like integrals, are actually, we call them linear operators. And so linear operators have these 2 properties. If you have the Laplace transform of a constant times a function, you can pull that constant out front and take the Laplace transform. You're familiar with this with derivatives, the constant multiple rule. If you take the derivative of a constant times a function, it's simply equal to the constant times the derivative of that function. And the derivative is also a linear operator. So here, the second property, the Laplace transform of a sum is equal to the sum of the Laplace transforms whenever those improper integrals converge. The derivative also has these properties, and so I want you to keep those in mind. That might help you in the future. If I ask you to take the Laplace transform of 3t squared, you know that that is equal to 3 times the Laplace transform of t squared. And now that you have these 3 built up already, we actually have some formulas you could work with for polynomials. So based on these, I want to point out the Laplace transform of AT squared would be 2a s cubed. So based on the linearity rule that we were just discussing, the Laplace transform of t squared is equal to t over s cubed. I won't make you verify that again. The Laplace transform of t is equal to 1 over s squared, and the Laplace transform of any constant is that constant over s. So the Laplace transform of 1 would be 1 over s. The Laplace transform of negative 7 would be negative 7 over s. This rule could actually extend, so I mentioned, I alluded to this a minute ago. If you have the Laplace transform of t to any power, then that's actually going to be that power factorial over s to the n plus 1, so s 1 greater than in the denominator. And I think that if you had been given some time, you could have built this rule by yourself. So the Laplace transform of a power function, we will always have this formula right here. And if you're interested, I might have you, if we had time in class, I would have you actually look at that for higher powers. What happens is each time you'll get this repetitive nature. And so that's why this property, the factorial, is occurring there because of the powers, the products over. Okay. So now we're going to find the Laplace transform of an exponential function, e to the at. A will be a constant here. I encourage you to pause the video and try a bit of this yourself. Once you're ready, I have substituted e to the at for f of t and my definition. So Laplace transform is defined to be this right-hand side, this improper integral. A is a constant here, and I know that I didn't make that clear on the slide, but treat A as a constant. Treat S as a constant, actually, since we don't know how to use it beyond that. Just treat S as a constant right now. So on this, inside this improper integral, I can go ahead and combine those two terms. You would find the sum of the exponents. I have written that, I realize, in kind of an odd way. So you might see up here, you'll notice you have at minus st. So you might think of that as quantity a minus s times t. I have factored out a negative, and I do have a reason for that. So go ahead and leave that there. I have e to the negative and this quantity s minus a all times t. To integrate that, I simply have, and it is an improper integral, so I didn't include the dummy variable b here, but you'll have negative 1 over that constant times e to the negative s minus at for the antiderivative. I will evaluate this at b as well as 0. When I evaluated 0, I simply get 1 times that constant. And you'll notice I factored it out front. Now, as long as s is greater than a, so I will be discussing s as a variable, a will just be a constant. So as long as s is greater than a, s is greater than a, then you'll have exponential decay here as b goes, so exponential decay here. So what I'm saying is this might be, if s is greater than a, this is a positive number, you'll have negative positive number times b, and then b is going to infinity. So if this is exponential decay based on this assumption, then this will go to 0, so that you'll be left with negative 1 times the ratio here, negative 1 over s minus a. So that will give me 1 over s minus a as my final result. The Laplace transform of e to the at will be 1 over s minus a. What I would like for you to do, so for a real number a is what I was using before, make sure that you understand how to find that Laplace transform, and also I want you to try finding the Laplace transform of s times at. S of at, sine of at. When you do that, I was thinking about it, you'll need to use integration by parts, and it is one of those wraparounds. If you will look at previous notes from earlier in the semester, we did that, and you added it into your notebook so that you could refer to it later. So pause the video and try to find the Laplace transform of sine of at. Now I've gone ahead and showed the two answers. We worked the Laplace transform for e to the at already, so this will be a set function, or a set definition that we use pretty frequently. And then the Laplace transform of sine of AT will be a over s squared plus a squared. If you have trouble with that, let me know. This is not a very, it takes a few lines of work. And so I mentioned pause the video, refer to notes from the beginning of the semester, how to evaluate that, and you should get the Laplace transform of sine of AT is equal to a over s squared plus a squared. Something else that I want to discuss, so for a function that is, this means, so when I say C2 class, so it is continuous and differential. The second derivative is also continuous and differential over all the reals. So for such a function, suppose that for a real number a that such that s is greater than a, the Laplace transform of a function is given by f of s. Now, also we're going to assume that f of t grows slower than exponential e to the st, so the exponential growth that we discussed earlier. So here we say, here I have, it says determine the Laplace transform of f prime and the Laplace transform of f double prime. What we will be doing is plugging in, so in my definition, I have substituted f prime here. And if we know that that has an antiderivative, because it was in the C2 class, then I have the antiderivative would be f of t times e to the negative st. So I've used integration by parts, so here would be my u v minus the integral of v du, and I have the substitutions here. Based on that, so we'll simplify a bit. I have that positive that cancels out. Since I know that this has a Laplace transform given by f of s based on my assumptions on the previous slide, I've rewritten that as f of x, so it's just the definition of the Laplace transform right there. I still need to take care of this a bit, so you do have an indefinite, so we would need to, an indefinite interval, so I would need to evaluate this at infinity. I've substituted a dummy variable there. Because f of t does not grow as fast as exponential function, this is why f of t must grow slower than e to the st, then that particular piece will go to 0. So as long as you've met that condition, and that is why we say f of t must grow slower than exponential function, then that term will go to 0 when evaluated at b, and when evaluated at 0, I will have f of t over 1, or I'm sorry, f of 0 over 1, which is what I have here. I still have s times f of s, so I've left that, and I've just reversed that so that we don't have a negative out front. I'm going to do this again for the second derivative. So I use integration by parts again. You'll notice here I have a Laplace transform of f prime, which I've already worked up above. On this left side, we are going to go ahead and evaluate that. Now again, because f prime does not grow as fast as the exponential, so when I've looked at this, so we're going to evaluate this, I'll have f prime of b over e to the sb. Now if f does not grow as fast as an exponential, then its derivative will also not. So assuming that f prime grows slower than an exponential function, then the limit of this will go to 0. I can plug in 0, this should be f prime of 0, and then that will take care of that will explain my first two terms. This s times what I had above, so I've substituted that in, and then when I distribute s, I'll have s squared times the Laplace transform of our first function, so f of x represents the Laplace transform of f of t, and then minus, I'll have an s times f of 0. F of 0 would be an initial value that we would have. Going ahead and putting that term there at the end so that you don't have a negative out front, we end up expanding that into this. If you're taking notes, I would write down what I have bolded. So Laplace transform of f prime is equal to this right side, the Laplace transform of f double prime is equal to this right side. You'll already maybe notice why the Laplace transforms will be very useful for differential equations where we have initial values, because immediately you'll be able to use those right away. You won't have to solve for constants, so that will take a step or two out of your work. If you were to continue this for your third derivative, you'll notice that a pattern again emerges, and so I wouldn't want you to continue this for higher order derivatives. It seems like we have enough to guess, or to suppose, you might say, that we have this property here. So for first order derivative, I have s to the first degree times the Laplace transform minus f of 0, so f just the original value. For the second order derivative, s squared times the Laplace transform minus s times f of 0 minus f prime of 0. So second order derivative, first derivative evaluated at 0 there. And for the third derivative, s cubed Laplace transform minus s squared f of 0 minus s f prime of 0 minus f double prime of 0, etc. So in general, for f, the derivative to the nth degree, then we will be able to expand that right side. This will be very useful again for initial value problems. And so in general, if you have a Laplace transform of a function's derivative to the nth degree, then you will be able to expand that using this property that emerged from what we were just looking at. I would like you to apply this idea to the initial value problem given here, indicated here. So this would be x double prime of t plus 3x prime of t plus 2x prime of t is equal to 12e to the 2t. I do have some initial values, and what I would like for you to do right now, I want you to write this first equation, and you will take the Laplace transform of x double prime. What I mean by that is the Laplace transform of x double prime. You could use this idea or go back to this case. So the Laplace transform of x double prime will be equal to s squared times the Laplace transform of x minus s times x to the 0, which we were given, minus x prime of 0. You'll also need to take the Laplace transform of 3x prime. Because you have a 3, you'll keep your constant, and the Laplace transform of x prime will be s times the Laplace transform of x minus x of 0. So you will substitute that in. You can distribute the 3, combine like terms with your previous term, and your last term here, the 2x, so you'll simply for this would have 2 times the Laplace transform of x. You might write 2 capital F of s, and then that all would be equal to 12 times e to the 2t. Now because you have a 12, you'll keep the constant, and the Laplace transform of e to the 2t would be the quantity 1 over s minus 2 based on our work from earlier. After simplifying the left-hand side and combining like terms and substituting our initial values, so x of 0 is 1, x prime of 0 is equal to negative 1, then you will have a statement, and you'll have a statement, combining like terms, you'll have the Laplace transform of x, or you might have written f of s. Once you solve for the Laplace transform of x, then you should have a rational function that looks something like this. So this function is entirely in terms of s here. This is the Laplace transform of x of t, but we often use f of s to denote this function because it relies only on s. This would be how to apply the Laplace transform to a derivative. Make sure you pause the video and give that some time and thought to make sure that that does make sense. I left a few of those steps out. So this video only covered the introduction of the Laplace transform and a few examples. With a bit more practice, we will be using these to solve differential equations. I didn't quite tell you how to solve the original differential equation here. We just developed something perhaps more confusing, but we'll get there. This would be like learning how to take logs of something, but we're not using the exponential function to get back where we started yet. So I do want to remind you, just like Napier used log tables, and in Cal 2 you may have used integration tables, we will have Laplace transform tables. These are found in the front cover of your textbook, the front or back cover of your textbook, depending on where that is, depending on which edition you have. So a couple things, you'll use this table of Laplace transforms. It may be in the back of your book, by the way. You'll use these tables to help you take the Laplace transforms of functions. In order to actually use the Laplace transform method to solve differential equations, you will need to be quite familiar with partial fraction decomposition. So I'm going to encourage you to review that before you do some of the homework. And what I mean by that is, here I have a quite complicated rational expression. When I want to undo this, I'm going to need the inverse of this Laplace transform then, and when I try to simplify that inverse evaluated of this, I will need to break apart those fractions. So partial fraction decomposition will be quite important for this section. This was just to introduce 7.1. There will be a homework assignment, and it is on Google Classroom to practice a few of these problems. So all we will be doing in this first homework assignment is using the Laplace transform. In the next video, I will discuss how to use Laplace transforms to solve differential equations.